happy Friday. Welcome to TVE Happy Math Hour, our weekly interactive math reviews for Math 1314 and Math 1324, presented by Yvette Chuca, Ruben Carizales, and Albert Isasi. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's events will be able to come and watch it. This session will provide the Handle Passport points, and the code will be posted on the chat towards the end of the session. So now at this time, please mute your mics for the best sound experience. Otherwise, the feedback could interfere with information we will be sharing. We'll be sending the 1324 room link on the chat so that you may connect to your session if you're here for Math 1324. Without further ado, I'll pass it on to our presenter so that we may begin.
Hello, everyone. Happy Friday. I'm just doing a mic check really quick. If you can hear me, please let me know. I'm using a different computer.
We can hear you.
Awesome. Okay, so today we're going to be changing to a new chapter, exponential and logarithmic functions. And so let's go ahead and get started. So an exponential function looks something like this, where your base is a number and then the exponent is a variable. So in the past, we've been working with functions that look like this, where we have the variable as your base, and then your number is an exponent. But for exponential functions, it's switched. So now your variable is going to be the exponent. Okay, so an exponential, so the A, we call it the base, and then the domain of F is the set of all real numbers, while the range of F is a set of all positive real numbers. But we'll look at the graphs in a little bit. So here's a problem related to exponential functions. Suppose you receive a penny on the first day of class, and then you get 2 pennies on the second day of class, and on the fourth day, 4 pennies on the third, and so on. If you do this every day until the 31st day of the month, what would happen? So the question is, would you rather take a lump sum amount of $1 million, or would you rather have a penny, and then the second day you have 2 pennies, and then the third day you have more pennies, and so on? Which of the two would you prefer? And so if we look at it a little bit closer, let's see what happens. So on day 1, you get 1 penny, and then day 2, you get 2 pennies, and then we're doubling each day. So on the third day, you get 4 pennies. So maybe the million is starting to look like the better choice. On the 7th day, well, we now have 64 pennies, but a million still sounds good. Okay, now if we continue this pattern, then on the 31st day, we would have 2 raised to the 30th day, and it actually would give you 1 million, this many pennies. So if we move the decimal 2 places to the left, then we're left with 10,737,418. So if you took $1 million, then you missed out on 9 million. But the idea here is how fast it grew to 10 million. So even though we started with pennies, if we're doubling each day, then it's going to increase by a lot. So that's the power of exponential functions. Okay. And so we're going to go ahead and look at these exponential functions. This is the basic graph. It's going to look something like this. And the base here is A. The number in front of your base is going to be your y-intercept. So in this case, your y-intercept is 0, 1. The domain, notice that we're using all the x values. And then the range, we're going from 0 to infinity. And of course, the y-intercept is 0, 1. This is considered an increasing function. And the horizontal asymptote here is the x-axis, which is y equals 0. And our graph is continuous. Okay. But something I want to note here is that the base is greater than 1. And that's important for later. Now, if you have exponential function where the base is between 0 and 1, then we're going to have a decreasing function. The y-intercept is still 0, 1, and the domain is still the same, and the range is from 0 to infinity. And now it's just a decreasing function. And so now let's go and look at another example. And so here you can see that your base, which is a half, is between 0 and 1. Now, if your base is just a number like 2, but you have a negative exponent, then it's still considered a decreasing function because we can change it to, we can rewrite it and the base would still be between 0 and 1. Okay, so we're going to go ahead and graph some of these. And so to graph it, we can construct the table like we did in chapter 1. So if I pick some numbers for x, if x is negative 2, and I plug it in for my exponent, we get 3 to the negative 2. To deal with this negative exponent, I can rewrite it as 1 divided by 3 squared, which is going to be equal to 1/9. And then if I plug in negative 1, I get 1 over 3 to the first power, which is 1/3. If I plug in 0, I get 1. And if I plug in 1, we get 3 to the first power is 3. So if we plot these points, here are my points. And if I connect them, then our graph is going to look like this. Okay. So notice that it's still similar to the first one that I showed you. And since my exponent is positive and my base is greater than 1, then we have an increasing function. And so now we're going to look at one-to-one functions, just a review from chapter 2. So if we have a horizontal line test, we have a vertical line test is used to determine if you have a function. A horizontal line test is used to determine if something is one-to-one. So for these exponential functions, if we draw a horizontal line, it touches in one place. That means that there's going to have these exponential functions will have an inverse. And these inverses are going to be the logarithmic functions, okay, which we'll talk about either later in this presentation or next week. One of the properties that we want to use is the one-to-one property, which tells us that for a greater than 0 and a does not equal to 1, if you have two exponential functions with the same base, then we can set the exponents equal to each other. So for example, if I have this equation, one of the things you want to look at first is if the bases are the same, which they are. We have a 10 and a 10. That means that we can use the one-to-one property. And that's going to allow us to set the exponents equal to each other. So this exponent is 2 minus 4x. This one is 6x minus 1. And we're going to solve for x. So I'm going to subtract 2 on both sides. And I'm subtracting 6x on both sides. So I get negative 10x is equal to negative 3. Divide by negative 10, so we get 3/10. Okay, so the one-to-one property allows us to solve these equations a little bit quicker. So let's look at this one. My base is 4, and I have a 64. So the bases are not the same, so I cannot use the one-to-one property the way that it's written. However, we can manipulate it so that they do have the same base. So in other words, 64, I can rewrite it as 4 cubed. And now I have 4 and 4. That means I can set my exponents equal to each other by using the one-to-one property. So I'm going to have x plus 1 is equal to 3. Subtract the 1. And we get x is equal to 2. Okay. So the next one. Again, the way it's written, we cannot use the one-to-one property, but you always want to ask yourself, can we manipulate this so that they do have the same base? And so here, let me just write, this right here is the same as 1 divided by 5 cubed. Okay, and so the bases are still not the same. So if I bring this 5 cubed up, I can do that. if I change the exponent to a negative, like I did here. So now we're going to have 5 and 5, that's the same base. And so I can set my exponents equal to each other. So we have x minus 3 is equal to negative 3, add 3 on both sides. So we get x is equal to 0. Okay, so for exponential functions, we have a special number, an irrational number. It kind of works like pi, but this number is e, and this number e is approximately 2.718. It's going to go on forever, and we call this number the natural base. And so the function f of x is equal to e to the x. When you see this e, they're referring to this number, 2.718, and so on. And so that's the natural exponential. And so if we were to graph that, it still looks the same. It has the same characteristics. Notice it's increasing. My x-intercept is at 0, 1. And that's because the base is greater than 1. It's 2.7 and so on. Okay, so if we have this equation, e raised to the x squared minus 3 is equal to e raised to the 2x. The idea here is to always ask yourself, do they have the same base? And they do have the same base. So once you see that they have the same base, then we can apply the one-to-one property, which tells me that I can take the exponents, x squared minus 3 is equal to x. So I'm going to go ahead and, since this is quadratic, I need to bring everything to the same side. So I end up with x squared minus 3. I'm going to take that 2x and bring it to the left side as well. So now this is quadratic, so you have choices. You can factor if it's factorable. Remember, not everything factors. Or you can use the quadratic formula. And so let's go ahead and see if it factors. So this is going to factor. So I set my factors equal to 0. And set each factor equal to 0. So my answer is x equals 3 and x equals negative 1. Okay. One of the things with exponential functions is that we can talk about compound interest. And so give me a quick. I'm sorry. Okay, so compound interest, we can use this formula. A equals P, parentheses 1 plus R divided by N, and then it's raised to the NT. So since my variables are exponents here, then I know this is exponential function. A is your future value, how much money you'll have in the future, or how much money you owe in the future, depending on what you're talking about. And then P is your principal, how much you begin with. R is your rate, interest rate. And we use a decimal to represent that. N is how it's being compounded, and then T is the number of years. Okay, so let's practice one of these questions. If you see that the problem says that it's compounded semi-annually, that means twice a year. Quarterly means 4 times a year. Monthly means 12 times a year. That means you're going to use 12, 4, and 2. And some might even say daily, which is 365, or some companies will use 360. And so we have N will be represented by those numbers here. Okay, if it says yearly, then you would use 1. Okay, so let's go ahead and try a problem. So find the amount to which 1,500 will grow if deposited in a bank at 5.75%. Interest is compounded quarterly for 5 years. Okay, so something we can do first is identify the variables. And so 1,500 is what you're starting with. So that's going to be your P. Your interest rate in a decimal, we move the decimal to the left 2 places. So we end up with 0.0575. It says that it's compounded quarterly. So quarterly means 4. So that's going to be N equals 4. And we're going to do this for 5 years. So T is 5. So we plug this into the formula. Then we get P is 1,500, R is 0.0575, N is 4, and T is 5. when you're doing these problems, 5 times 4 is 20, so you would have your 20 here. And then you want to do the inside of the parentheses first, and then raise it to the 20th power. And then the last thing you do is multiply by 1500. So sometimes I've seen people multiply 1500 into the parentheses first, but remember that you have to take care of that exponent first before you can multiply. So we end up with 1,995 with 55 cents. So if you're looking to retire, this is not the best investment. Okay, so there's other tools, vehicles that you can use. Some of them are like annuities, for example, but this is just using compound interest. So here's another problem. A couple just had a baby. How much should they invest now at 5.8% compounded daily in order to have $35,000 for the child's education 18 years from now? Assume 365 days in the year. Again, this is we just have to be careful here because sometimes banks will use 360. Okay, so it says how much should we invest? So we don't know how much we're gonna invest, so that's gonna be your P, is what we're trying to find. So that means that at the end of all this, you want to have $35,000. So A is 35,000. The interest rate is 5.8%. So this looks like we did it with the previous interest rate. And then, so I'll check right now to see if the problem continues with this rate, or maybe we just round it off. So then the compound interest is 365, and then T is 18. Okay, so the problem is correct now with using 5.8%. So just not to confuse anybody, this should have been, let me just scratch it off. This should be 0.058. Okay. So you might be thinking, well, if you round, it'll be the same. But when you're dealing with money, you don't want to round to the end because you'll lose some money in there. Okay. So you have 35,000 is equal to P, 1 plus your interest rate divided by 365, and 365 times 18. And so 365 times 18 is 6,570, and 0.058 divided by 365 is this number. And notice that I'm keeping all my decimals. And if you're doing problems on WebAssign, you don't want to round at the beginning, always round at the end, because then the problem's going to count it wrong. So make sure that you're using all these decimals. Usually if you have your calculator, you can just see them there and go to the next step. So like here, I would just press +1, and then I would raise that to 6570. And that comes out to 2.840, so on. Again, I'm not going to round till the end. I'm going to divide by that number on both sides. And so I end up with 12,322.55. And so that would be what the couple should invest if they want to have their $35,000. Again, this is in a compound interest. They could probably invest it in a different vehicle and have more money for sure. Okay. So these were just some applications. We already talked about the first one. One of the things that we were looking at is if it's compounded daily, that's 365. And so eventually they said let's do continuous compounding. And that formula is A equals P. E is your number, that natural number, and then raised to the RT. And so it works similar, except it's not compounded daily or monthly. It's now just continuous compounding. Okay, so those were your two equations that you might run into. So for section 3.2, earlier I said that exponential functions have an inverse. And so the logarithmic function has is the inverse to that exponential function. And so here we can see the exponential function right here. And its inverse is this one that is going this way. Okay, so the domain for the logarithmic function is from 0 to infinity. And then the range is going to be negative infinity to positive infinity. So the common log is log x. Notice here it's missing. Normally, let me just backtrack a little bit. When we're doing logs, normally you'll see it like this. You have log, and then they'll have a little number right here, and then you'll have some other number over here. If your base, this little number here, the 4, that's what we call the base. If this is missing when you're doing the log, then what that means, so for example, over here, I don't see a little number here. That means that the base is going to be 10. Okay. So anytime you see a log without this little number, then that means that it has a base of 10. And we just don't write the base of 10, but it's assumed to be base of 10. And the reason, well, if it's base 10, then you can use your calculator. That means in your calculators, if you look at the calculator, you see the word log. That means that it's a base 10 log. And then for the natural log, we write it as ln x, and that just translates as log with the base e. Okay, so instead of writing log base e, we write ln, and this is an L. Sometimes people think it's an I, so they'll get the problems wrong on WebAssign because they enter IN, but it's LN. Okay, so we're gonna do some problems here in a little bit. So it says one of the things that we want to do is convert from log to exponential, or from exponential back to log. So it says write the logarithmic equation in exponential form. And the reason we want to be able to do this is to be able to solve for x. Okay, so here we have log base 4 of 16. Okay, so to convert, we're going to go ahead and do this. So this is one of the sentences I like people always remember. The log, which is this whole thing, is always equal to the exponent. So I have log 416 is equal to x. That means that x is going to be your exponent. So your base is 4. So we write it as our new base for the exponential function. The exponent is going to be whatever the log is equal to, in this case x. And then your other number would be 16. They don't want you to solve it or anything like that. They just want you to rewrite it from log to exponential function. So let's try this one. So first, you want to make sure you identify your base. So here's my base is 5. So I would write 5. And then, well, let me start over. Let me erase that. Okay. This is written in exponential form. So you want to change it to a log. So since I want to change it to a log, I'm going to write log. Okay, then I need to identify my base. So my base for this is 5. So 5 is going to be my new base. So I put that down for my log. And then I'm going to have some number, and this is going to be equal to something. So the log is always equal to the exponent. So my exponent is 3. So that's what my log would be equal to. And then your other number is what goes in the parentheses. Okay. So let's try this one. So this one is written as a log. So we need to convert it to exponential function. So first we identify the base. So my base is b. So I'm going to write it as b. And then the log is equal to the exponent. So this whole log is equal to 3. So that's going to be my exponent. And then that's equals. to our other number, which is 27. Okay. And let's continue. We have one more. So we have square root of 81 is equal to 9. So in this chapter, whenever you see square roots, we're going to be changing them to exponents just so that we can work better with them. So anytime you have a square root, that is the same as having an exponent, and that exponent would be a fraction of 1/2. And the reason it's a half is because this is a square root. So the root is 2, so we have a half. If you had a cube root of, let's say, 81, then that's the same as 81 to the 1/3. Okay, so this root is going to be your denominator in that fraction. So if you have to the fifth root, then it would be 81 to the 1/5. Okay, so let's go ahead and change this. So I'm going to have 81 raised to the power of a half is equal to 9. So this is exponential. So we want to convert it to a logarithm. So I'm going to write the word log first. And then we're going to identify what the base is. Okay, so my base here is going to be 81, right? And so we're going to write our base, 81. And then we're going to have some other number here, and this is equal to. So the log is always equal to the exponent. In this case, the exponent is a half. So I write my half, and then my other number is 9. Okay. And so let's go on to the next one. So we're going to be using properties, and then eventually these properties will help us solve equations. Okay, so these are just the properties that are listed here. You have log a of 1 is equal to 0. And just to give you a quick example of that, let's say you have log of 3, and then you have 1, and you want to know what is this equal to. Okay, so if we convert it to an exponential, my base here is 3. So I'm going to write 3. The log is equal to the exponent. That means that my question mark is my exponent is equal to 1. Okay, so if we ask ourselves, what does that question mark have to be in order for me to get a 1? And the only choice I have is the power of 0, because anything raised to the 0 would be a 1. And so anytime you see this, our answer is going to be 0 because of that reason. So you could have, for example, log of 1 million, which is a big number. So let me just finish writing a million of 1. And so without doing anything, since you have log of a base of the number 1, then automatically you know that that's going to be 0. Okay, so that's what this property is saying. The next one, log a of a is equal to 1. So just to show you an example of that one, if you have log of 3 and you have the same number here, 3, and you're trying to figure out what this is equal to, then we can change it to exponential. So my base is this 3 here, and the log is always equal to the exponent. So my exponent is this question mark, and then I have this other number 3. So in order for 3 question mark to be the same as 3, that means that the question mark has to be 1. And so that's where we get this property here. If the bases are the same, then you get a 1. And then we have the other bases here. The fourth property is one that if you can use it, then it's easier to work with. And this is just saying that if you have a log with the same base, then you can set x equals to y. Okay, so I think we have some examples here. It says use properties to solve. Okay, so I think we have some examples here. It says use properties to solve. Okay, so here we want to find out what is log base 3 of 1 over 27. And then I have a question mark. So we're trying to figure out what that is. And so there's different ways to solve this. One way is to convert it to exponential form and then solve it. And then the second way, we can use the properties. Okay, so let's convert to exponential form. So my base is 3, and then I have the question mark, equals 1 over 27. I want to see, could I use the one-to-one property? Well, they don't have the same base, but 1 over 27, we can rewrite it so that it has a base of 3. So remember, 27 is 3 cubed, but if I bring it to the numerator, then I end up with -3. So now they have the same base. That tells me that my answer here is going to be -3. Okay, so we can use a one-to-one property. We bring the exponents to down, so the question mark and the -3, so my answer is -3. Okay, if you want to use the properties, then we can, let me go back. We can try to manipulate this 1/27th. I can write it as 1 divided by 3 cubed, which is log of 3. And then if I bring this to the top, we get 3 to the -1. So now you have this base and this base. And so if we use the properties, which one will resemble our problem here? And so here you have the two bases are the same. So your answer is that exponent, -3. Okay. All right, so let's try this one. Let me go back really quick. Okay. So use properties to solve. So we have log pi of pi to the 5th power. And so you would ask yourself, which property, is there any property there that I think would work in my situation? And so the bases are the same. So what do you think our answer is going to be? Okay, so let's check. So the bases are the same. And so that means that we can use the same property here. So my answer would be my exponent, in this case, 5. Okay, let's try another one. Log of 7.5 of 1. So again here, if we look at this, then we want to know which property we might be able to use. And so let's look at them. So here I have a 1. That means my answer would be 0, right? 0. Now let's say, well, Ms. Chuka, these are a lot of properties that I might have to remember, okay? The good news is if you forget these properties, then your other option would be to convert this to exponential function. So my base is 7.5. And I know that the log is the exponential, the log is always equal to the exponent. I don't know what the exponent is, and then I would have my 1. So by looking at this, then 7.5 raised to the 0 power would be the 1. So that's how we can get 0 here. So you don't have to memorize all these. You can just change them to exponential, and then that would help you to see the answer as well. So here I have my bases are the same, okay? And so which property can I use? So we have that these are the same, so my answer would be 1. Okay, so we have 1. And then now we have 3 log 3 of 8. And so here my base is 3 and the log base is also 3. So that means we can use property number 3 right here. And your answer would just be x in this case. So in this case, your answer would be 8. Okay. It says use a definition of logarithm you can solve equations involving logarithms. So if we wanted to solve for b here, then what we can do, since b is the base, it's kind of trapped in here. So we can change it to exponential form. So b raised to the third power is equal to 1,000. And so now I can solve for b, right? And so here we get that b is 10. Because 10 cubed would be 1,000. Let's try this one. So now I want to solve for x, but x is trapped in here because of the log. But if I change it to exponential form, I get my base is 6. The log is equal to the exponent. So in this case, 5 is my exponent. And so now 6 to the 5th power is equal to x. That means that x would be 7,776. And so from converting from one form to the other can help us solve these equations. Okay, so these are all just properties. We've looked at the first 4. And then number 8 is a one-to-one property, which if they have the same base, then we can set m equals to n. Examples 5, 6, and 7. I don't think I have them in this presentation, but they'll probably be in the next week one. But let's see what we have next here. Okay, so let's look at this one. Solve for x. So we have log 5 of x plus 1 is equal to log 5 of 9. So one of the things that we can notice here is that they have the same base. Okay, and that's good news because we can use the one-to-one property, which is down here. And that one-to-one property tells us that we can set x plus 1 equals to 9 because they have the same base. And now we just solve for x, subtract 1, so we get 8. Okay. When you have logarithms, you always want to check your answer because remember that the domain for logarithms is from 0 to infinity. And so to check your answer, we're going to take x equals 8. And if I plug in 8 here, I would have 8 plus 1 is 9. So whatever you have inside of this parentheses, this number in here should always be greater than 0. Okay, so you always want to make sure. So if you plug in 8, 8 plus 1 is 9, and that's greater than 0. That means that x equals 8 is going to be a solution. Okay. Let's try another one. Log 17 is equal to log x squared plus 8. So the base here, I don't see the little numbers, but that's okay because that means that the base is 10. So they both have a 10 here. We just don't write it. Have a 10 here. We just don't write it. Okay. Now the important thing is that they have the same base, which now tells me I can use the one-to-one property. And I can say 17 is equal to x squared plus 8. Notice that it's quadratic, so we're going to need to put, I can subtract 8 on both sides. And I get x squared minus 9. I can use the square root property, so I'm going to take 9 back. And to solve for x, I'm going to take the square root on both sides. And so I get x is equal to plus or minus 3. Okay, always check your answer. So if you plug in 3 for x, you get 9 plus 8 is 17, so we're okay. And if you plug in negative 3, we still get 9 plus 8 is 17. That means that these are both solutions. Okay, so again, we're plugging in the x's here, and whatever you get has to be greater than 0. Let's try one more. Natural log of x squared minus 3x is equal to natural log of 18. They both have a base of e, so that means that I can set this equal to 18. Notice it's quadratic, so I need to have everything on the same side. So x squared minus 3x minus 18. At this point, since it's quadratic, you can factor or use a quadratic formula. This one factors. So my answers are x equals 6, or my potential answers are x equals 6 and x equals negative 3. We're going to check our work. So if we plug in 6, we get 36. minus 18, it's going to be positive in here, so that's okay. If we plug in -3, we get 9, and then that's going to be a plus 9, so we are okay. So they're both solutions. Hopefully I have one that's not a solution so you can see why it's not a solution. Okay, so here, solve for x. So we're going to go ahead and go here. This does not look like any other properties that we've looked at so far, which is 1 through 4. So in section 1.3 or 3.3, we're going to use the remaining properties, which are these right here. And we're going to use these properties to manipulate these properties here. Okay. And so for this one, if you notice that property 5, it says log b of m times n. If you're multiplying, we can separate them as log b of m plus log b of n. So if we look at this, we're adding these two together. So that came from multiplying them together. So this problem, and next week we'll go into more details about it. But for now, I'll go ahead and work it out. So I can rewrite this as log, and the base is 4. Okay, and so I'm multiplying these. So now I'm going to have x plus 6, times x minus 6, and then this is equal to 3. Okay, so from here, then we can still check to see if we have any logarithms that we could use, right? Or any properties that we can use. We really can't, but what we can do is we can change this to exponential form. If you want, you can multiply these two together, but for now I'm just going to leave them like that. And so what I'm going to do is I'm going to change it to exponential form. So my base here is 4, so I'm going to write 4. Okay. The log is always equal to the exponent, so this log is equal to 3. So that means that my exponent is 3. And then I have the rest of this stuff. Okay, so I have x plus 6. And I have x minus 6. Okay, so now it just becomes a problem that we can solve. So 4 times 4 times 4 is going to be what? I'm going to come back up here where I have some space. So I'm going to have 4 times 4 times 4 is 64. And I guess we'll multiply this out because it's going to be quadratic. So x times x is x squared. And x times -6 is -6x. And 6 times x, positive 6x. And 6 times -6, -36. Okay, so if we gather our like terms, we get 64 is equal to x squared. These are going to be 0 minus 36. Okay, so it's still quadratic, but I only have an x squared term, so I can add 36 on both sides so that I can isolate my x squared. And so we get x squared is equal to 100. Okay. So now that I have x squared equals 100, how do I solve for that? So we take the square root and we end up with x is equal to plus or minus 10. Okay, so that is my possible solutions. I need to double check. So if I enter, okay, so that is my possible solutions. I need to double check. So if I enter a positive 10 in here, I get 10 plus 6 is 16. 16 is greater than 0, so we're good. If I enter positive 10 here, 10 minus 6 is 4. 4 is greater than 0, so we're good. That means that x equals 10 is a solution, and then we need to check negative 10. So if I plug in negative 10 for x, I get negative 10 plus 6 is negative 4, and that is not greater than 0. That means that x equals negative 10 is not a solution. So your only solution would be x equals 10. Okay. So next week, we'll be looking at more properties, mainly 5, 6, and 7. And then we'll go ahead and do some more problems. We'll be converting back and forth as well using the properties and then solving for some of the equations. So this was more 3.1 and 3.2. And that's all I have for you guys today. But next Friday, we'll continue with this chapter.
Thank you, Ms. Chuka, for your wonderful presentation. We do want to remind you all about our previously recorded sessions, which are available on a YouTube playlist. Today's session will also be available on the playlist later on today. Also linked is a short survey to help us improve our TVE sessions. Please take time to fill out the survey. Before you leave, I want to share the TVE sessions that we will have next week. We will be back with Happy Math Hour next week, where Math 1314, like Ms. Chuka said, will be covering more properties of logarithms, exponential, and logarithmic equations. And Math 1324 will be covering basic matrix operations. At 1 today, we will have a student success, and the topic will be origami. Thank you all for coming in today. We hope you all have a lovely weekend. If you have any questions, feel free to use the chat box or mic. And just a friendly reminder, remember that we'll be off on Monday. Thank you guys and have a great weekend. Bye-bye.